to week 14. In this week, we'll be looking at multi-threading issues and the solutions we can apply. So by the end of this lecture, you should be able to implement multi-threaded Java programs in a thread-safe manner. Also, you should be able to implement simple producer-consumer problems using guarded blocks. So when talking about multi-threading issues, there are two prominent problems: thread interference and memory consistency errors. In order to understand what thread interference is, let's look at this simple example. So here we have this class counter. Inside it, we have this integer variable c. It gets incremented inside the increment method and gets decremented inside the decrement method. Now, although there's one line of code to increment or decrement this integer variable at the high-level Java program level, actually, when we try to execute this at the hardware level, that means the assembly level, this task is broken down into multiple subtasks. In general terms, we can say, for example, if you want to increment an integer variable, first that value has to be read from the memory and then copy to the thread's local cache. And then within that local cache, this value is incremented. And after that, this incremented value is written back to the memory. The same happens when we want to decrement the value. So now suppose we have two threads, thread A and thread B. And thread A is incrementing this variable C and thread B is decrementing this variable B. So let's assume thread A executes before thread B. What will happen? What will be the last value? So we start with the value 0 for the variable. So first thread A will start executing. It will copy the value that is already in the memory, which is 0. Copy it to the thread's local cache, increment it by 1, and then copy back this value to the memory. So now the memory location for this variable will have the value 1. Then thread B executes. Similar to the previous thread, it will copy the value from memory, which is now has the value 1, and then increment it within the lower thread's local cache and then write back to the memory. So at the end of execution of thread A and thread B, the variable C will have the value 0. So if you execute thread B and afterwards thread A, the same value will be there for the variable, that is value 0. Now, as I told you, incrementing or decrementing even a simple variable at the hardware level is broken down into multiple subtasks. So there is no guarantee that the thread will be able to continuously run until all these subtasks related to a single line of code in your Java are executed. So in other words, if you remember, we learned that threads get scheduled because there are a lot of threads in the computer, and to give a fair chance to all the threads, the scheduler selects a subset of threads that are running at a given time. So that means while a thread is in the middle of incrementing or decrementing a variable, it can get scheduled. The possible scenario is shown here. So now we start with thread A, which starts first, and it retrieves the value from the memory. And immediately after that, it is sent to the runnable state by the scheduler. Then thread B is started. It also reads the value from the memory. Now, although thread A read the value before, it did not have chance to write the new value to the memory. So as a result, when thread B accesses the same memory location of this variable C, it will also see the value 0. So that is what it will be copied to its thread local cache. Now thread B gets scheduled and thread A gets a chance to run. So it adds 1 to the current value of this variable, and again it is sent back to the runnable state by the scheduler, and thread B is given the chance to run. So then thread B will carry out its operation by subtracting the value. So now it is -1 at the thread local cache. Now thread B gets schedule. And then thread A gets a chance to run. So what does it do? It carries out the final step. That means the updated value is now recorded in the memory location. This value is now in the memory is set to 1. Now again thread A is now in the runnable state. So thread B gets the chance to run. So now thread B does not know about this thread A's interaction with the same memory location, because when thread B read the value from the memory location, thread A has not yet updated its value. So when thread B finishes the execution of the storing value, the memory location corresponding to this variable C will have the value -1. Now previously we were getting 0 and now we are getting a totally unexpected wrong value. What has happened here? The value written to the memory location by thread A has been completely overwritten by the value written by the thread B. So, and don't get confused and assume that after every action at the hardware level, the thread gets scheduled. No. So we never know, or thread does not know when it will get scheduled. So sometimes the thread may be able to carry out all these 3 actions and then it will get scheduled, and sometimes it may get scheduled after doing 2 actions or maybe 1 action. So how it happens is not directly known. It is up to the scheduler to schedule. And here what I have shown is just an example of an extreme case that will happen. So as you can see now, the value written to the memory location by thread A is completely overwritten. So this problem is called the memory consistency error. In other words, the memory is in an inconsistent state. Why? The change done by thread A is not visible to the thread B. So to solve this problem, we have to guarantee that these threads do not operate on the same memory location at the same time. So if a memory location is accessed by more than one thread at the same time, at the, in an overlapping time period, we say this is a shared resource. Or now in our case, in the example, the variable C is a shared resource. So when there is a shared resource that is shared among multiple threads, the only way to guarantee that there are no memory consistency errors and no thread interference is to make sure threads are operating on this shared resource one after the other. This we call the happens before relationship. So in the previous example, if thread A happened before thread B, or if thread B happened before thread A, we would not have this issue. So how can we guarantee that? So by default, in the Java execution environment, there are many places where happens before relationship is guaranteed. For example, if you have a single threaded application, everything that happens within the thread is following one after other. So this happens before relationship is there. And object initialization, everything that can be done by the thread or on the thread is happening after object initialization. In other words, object initialization happens before any action carried out by the object. And similarly, a thread. The thread start should happen before the thread can carry out any meaningful action. Similarly, join. So after calling the join, the thread calling that join method will not do anything until the other thread has completed its task. Now, if you want to guarantee such kind of happen before relationship on when we access a shared resource by multiple threads, we have to explicitly do that. We do that using a mechanism called synchronization. That means we are explicitly synchronize threads to operate one after the other on a shared resource. Let's see how it is being done. So there are actually 2 methods to synchronize. First is synchronized methods, the other is synchronized statements. So here we show a synchronized method. So all you have to do is to add the synchronized keyword to the method. Now don't go and blindly add synchronize the keyword to all the methods you have. You must synchronize a method only if it contains a shared resource. Now here in our example, our variable C is a shared resource that is accessed by multiple threads. So because of that, the corresponding methods are synchronized. So what happens when the methods are synchronized? So when we synchronize method, it guarantees the object that carries these methods will not be accessed by multiple threads at the same time. In other words, the operation on this object guarantees a happens before relationship for the threads. Now let's look at this example. Now I have two shared counters, SC1 and SC2. So they are both created using our shared counter class. So from the same class, we are creating two objects. Now there are two separate objects. Suppose thread A operates on SC1 and thread B operates SC2. There is no concept of a shared resource here. Why? SC1 is operating on one object and SC2 is operating in the other object. So we don't have to worry about synchronizing. The synchronizing is needed in the second case. That means both SC1 object and SC2 object are accessed by both thread A and B. So if this can happen, that means SC1 and SC2 access by thread A and B can happen at any time. That means the methods are not synchronized. So this may lead to the memory consistency errors, which is a major issue in multithreading. So in order to avoid that, what we can do is we can add synchronization to the our synchronized counter class, so that when the SC1 object and SC2 object are accessed by different threads, the access is synchronized. That means it happens before relationship is guaranteed. For example, as you can see here, SC1 is first accessed by B and after that A accessed, and SC2 is accessed by A first and then B. So of course this is not the hard and fast execution. For example, SC2 can be first accessed by B and then A, and then again after it can be accessed by A or B. Likewise, multiple threads can access the same object at different times, but what it guarantees is when one thread is accessing this object, it has exclusive right to this object as long as we have synchronized this object via methods. So when we added the synchronized keyword to a method, that means when we have a synchronized method in our application, it uses a lock. So that means when the synchronized method is called by a thread, the lock corresponding to this object is exclusively given to that thread that is accessing this synchronized method. So this lock is called an intrinsic lock. Every object by default is given an intrinsic lock. So when we use the synchronized method, we don't have to explicitly create a lock for that object. This lock is automatically created by the Java runtime environment and given to the thread that is accessing a synchronized method in this object. So when an object holds the lock, when a thread holds this lock, no other thread can access or own this lock. In other words, at a given time, a single thread can own this lock. So this guarantees the happens before relationship. So if we go back to our example of synchronized method, so let's try to understand what happens here. Now, suppose thread A gets into the synchronized increment method. It is accessing only one method. So let's say we consider the SC1 object. So from this SC1 object is created. Now the thread 1 accesses the synchronized increment method of the SC1 object. Then the whole object is exclusively locked and given to the thread A to access. So after thread A finishes executing this synchronized increment method, the lock is released from A. So while the thread A is accessing this synchronized increment method, the lock is exclusively given to thread A and no other synchronized method can be accessed by any other thread. So in other words, thread B cannot come and decrement the counter while the thread A is incrementing the counter. So that means happens before relationship is guaranteed and memory consistency errors are avoided. So however, so now here what we saw was very simple methods. But in reality, your methods will be more complex. It will contain different access to different objects and maybe multiple shared resources. So if you lock an object at the method level, while a thread accesses this long-running method, no other thread can do any other thing on this object. So this will reduce the concurrent capabilities of your application. Because of that, we have to introduce fine-grained synchronization. So that means we are introducing synchronized statements. So remember, in Java, what we have is re-entrance synchronization. That means, so when a thread is having a lock, no other thread can acquire that lock. However, a thread currently holding the lock can reacquire the lock if it wants. So here's an example of a synchronized statement. So instead of adding the synchronized keyword to the method add name, we have added the new block, which we call the synchronized block. So synchronized block is added using the synchronized keyword. And remember, unlike in the synchronized method, when we use a synchronized statement, we have to explicitly indicate the object that we are going to use as the lock. So remember what I discussed earlier. So every object has a lock associated with it, which we call an intrinsic lock. So when the synchronized keyword is added to the add name method, what is used is the lock of this corresponding object. However, when we add the synchronized statement, we can explicitly mention what lock we are going to use. So by lock, I mean just adding a reference to an object and then the lock associated with that object will be used as the lock. So here when I pass this keyword, what is the object we are using here and where is the lock? So if you remember that this keyword refers to the current object. So when you are using the synchronized statement with the parameter this, that means we are using the lock of the current object. So more or less this is same as your synchronized method because now the object lock is used. However, if you use this object lock, it is a problem if you have multiple shared resources within the same object. For example, if you look here, now instead of one shared variable, we have two variables, C1 and C2. Now C1, updating C1 does not have any impact on updating C2. They are two independent resources. So if you just use the object as the lock, like we did here, or the synchronized keyword in the method, what will happen? There is one lock for the whole object. So when one thread is accessing the C1 resource, no other thread can access even the C2 resource. So which is not a good design. So normally when we are using the synchronized statements, instead of using the objects lock, we can define our own lock. So how do we define a lock? It's very simple. We create some arbitrary object. So the simplest is to create an object of type object class and then use that object as our lock. So now here, if you see, we have two synchronized statements, each taking a different lock. So lock 1 is handling the variable C1 and lock 2 is handling the variable C2. So what does this mean? So if thread A comes and wants to access the C1, it will call this synchronized statement and it will acquire the lock corresponding to this lock 1 object. And only the synchronized statements that are locked using the lock 1 object will be exclusively allocated for thread 1. So while thread 1 is operating on this C1 variable by acquiring lock 1, thread 2 can come and acquire the lock 2. Why? Because it's a separate lock. No other thread has taken the exclusive access to it. So thread 2 can lock the lock 2 object and operate on the C2 variable. At the same time, lock 1 is captured by the thread 1 and it is operating on the C1 shared resource. So no problem. So as you can see, with synchronized statements and multiple locks, we can have more fine-grained access to shared resources. This will increase the level of concurrency in your program. So this is a very good thing. So earlier we started with the single-threaded application, and then we realized single-threaded applications cannot do much. So to increase the concurrency level of our program, we introduced multiple-threaded applications. So and when we are using multi-threaded applications, we came to a problem. What is that problem? When multiple threads are operating on the same memory location or same shared resource, there can be memory consistency and thread interference issues. In order to avoid that, we introduce a locking mechanism, which we call synchronization. So now it is fine. Now when a thread is accessing a shared resource, it gets exclusive access to the shared resource. However, sometimes when you use such shared resources and explicit locking mechanism, there can be other problems. For example, deadlock. Deadlock is considered as a liveness problem in multi-threaded applications. So there are other liveness problems such as thread starvation and Livelock. So let's briefly look at these liveness problems as well. So deadlock is something very familiar to us. So as we can see here, in this four-way junction, no vehicle can move. So we can say the vehicles are in a deadlock. So what has happened? B is blocking A, and C is blocking B, and D is blocking C, and A is blocking D. So A can't move because B is blocking, and A is also blocking D. So no one can do anything meaningful. Everyone is stuck. So this is the same situation when a deadlock happens in a multi-threaded application. So remember, for a deadlock to occur in a multi-threaded application, there should be more than one shared resource and more than one thread. Now see what has happened here. Thread 1 has exclusive access to object 1 and it wants to access object 2. Similarly, thread 2 is having exclusive access to object 2. Now it wants object 1. No thread can proceed because it is holding on to a lock and without releasing, it requests the other object. So this is the simplest scenario where a deadlock can occur. In real world applications, there can be more than 2 shared resources and there can be more than 2 threads. So in such cases, the deadlock situation is more complex. Now let's look at an example of this issue. Now, as you can see, we have a bank account class, and there it has a method called transfer. For simplicity, I have shown only part of the code. Now, transfer method takes two parameters, the from account and the to account. So now within the transfer method, what happens? It first lock the from object. That means it has exclusive access to the from object, and while holding that from object, it wants to lock the to object as well. So now let's see how a deadlock can occur in this situation. Now we are creating two threads. So again, the thread creation I have shown in two different examples. First one is what we learned earlier. We created a T1 thread and then we start it explicitly. So what is happening in T1? So when the T1 thread is running, it uses the transfer method of the bank account class. Now remember, transfer is a static method, so it can hold on the class itself without any object. So now T1 calls the transfer method. The from account is the full account we have created here, and the to account is the bar account we have created here. So when T1 is running, what will happen? It will first lock the full account, and while keeping the lock of full account, it will try to lock the bar account as well. If only thread T1 is there, then there's no issue. It has exclusive access and it will run. And in fact, if there's no other thread, there's no need to lock as well. So now in this case, we are not having only one thread, but we are creating another thread as well. So altogether, when both threads are started, along with the main thread, we have 3 threads in the class. However, only the threads we explicitly create will be accessing the full account and the bar account objects through the transfer method. That's what we have shown here. So now again to repeat, our thread T1 is first locking the full account, and while holding that lock, it wants to lock the bar account. Now in the second thread, which I have not explicitly created the thread, but I am creating the thread object in an anonymized manner. So let's call this the thread T2. So what happens in T2? It takes the two accounts in the reverse order. So T1 takes full account and bar account. T2 takes bar account and full account. So when executing the transfer method, T1 is holding the from object lock and trying to obtain the lock corresponding to the to. That means first the thread 1 holds the full account lock and tries to obtain the bar account lock. And what happens in our thread T2? It holds the, or it first locks the bar account, and while holding that lock, it wants to lock the full account. Now, thread 1 holds full account, wants to lock bar account. At the same time, thread 2 has locked the bar account, wants to lock the full account. So this is the exact situation we have shown here. Each thread is holding one object lock and wants to access the other object as well. So here, none of the thread can proceed because no one is going to release the lock they are holding according to this code. So as you can see, we will have to explicitly handle such situations. The challenge is sometimes this kind of scenarios will not be easily captured. So when you implement your multi-threaded applications, and especially when you are using the synchronized statements or method, carefully check whether when you have multiple threads and multiple resources, whether your locking mechanism can lead to deadlock. And starvation is another problem that happens when you have multiple threads, especially there are threads that are having different priority levels. So sometimes there's a shared resource, and when threads are selected to access the shared resource, the scheduler usually gives priority to the high priority threads. So suppose there's a shared resource which is being accessed by a large number of threads, and if most of these threads have been set to high priority, always when thread is is given chance to the threads to access the shared resource, this high priority thread will be getting the access one after the other. So which means if there are low priority threads waiting to access this shared resource, they will not get chance. So which we call thread starvation. That means the thread is starving to access the shared resource. So thread synchronization can lead to starvation as well. Why? Now there's a shared resource. When one thread is locking this shared resource, all the other threads are now blocked and waiting to access. So again, now I'm introducing a new term, block. So suppose one thread is accessing a shared resource and it has got the exclusive access to this object by acquiring the lock. Now, if another thread comes to access this object, it cannot access because it is now locked by the previous thread. So we say the second thread goes into the blocked state. Remember, a thread has multiple states. So in this case, if a thread is trying to access an object that is already locked by another object, the second thread goes into a locked state. So if there's a shared resource, and if a thread is having exclusive access, all the other threads that come to access this lock will be in the lock state. So suppose there are multiple threads waiting, and when the scheduler gives a chance to one of the lock threads to access after the first thread completes, the thread will always go for a high priority thread. So if a lot of high priority threads are waiting, whenever the scheduler gives a chance to access the object in an exclusive manner, all these high priority threads now will be getting chance. And if there is a low priority thread waiting, it will not get chance to access this shared resource. So we say the low priority thread is now being starved because it does not have a chance to access this shared resource. So in our simple applications, it is bit difficult to implement this problem and see how the starvation affects our multi-threaded program. However, you can give it a try. So you can create multiple threads and give them different priorities, and you can run them and see whether each thread is getting different or similar chances. So if you are lucky, you will see that high priority threads are getting more chances compared to the low priority threads. The final problem we have in multi-threaded applications is Livelock. So deadlock and Livelock. So keep in mind, the deadlock can occur only when there are more than one shared resource and there are more than one thread trying to access these multiple shared resources. In contrast, Livelock can happen even when there is one thread also. Now here we are showing an example related to two threads. Now suppose you are walking on a very narrow corridor and another one comes face to face. Now one has to get to the side for the other one to pass. So you move to left side. The other person also moves to left side. You move to right side. The other person also moves to right side. So you keep on moving to left and right, and the other person also does the same. So you are doing something, but you are not progressing. So that is what we mean by Livelock. Threads are running, however, they are not doing anything meaningful. So this is different to deadlock, where in deadlock, the threads are not doing anything at all because they are in a deadlock. So finally, we are going to talk about the concept of guarded lock with respect to shared resources. Now, the locking mechanism guarantees the exclusive access to a shared resource for a thread. However, sometimes when multiple threads are operating on a shared resource, they need to coordinate their access. In other words, they have to make sure there is a particular value in this shared resource for them to proceed. So let's look at an example. So suppose there is a shared resource and this shared resource must have a particular value for this thread to contain. So this guarded success method depicts that situation. So while this success is not set to true, our thread has to wait. So only when success is set to true by say another thread, this current thread can proceed. But what is the problem of this kind of a situation? The thread is continuously checking the value of success. This situation we call busy waiting. In other words, we have a thread that is busy waiting and wasting the computation time. So the solution is to introduce a guarded block. So here the guarded block, what it does is, rather than making a thread to busy wait, the guarded block will send the thread to a wait state. Now here we learn the final state of the thread. So what are those? Running, runnable, sleep, block and wait. So blocking happens if a thread is trying to access an object that has already been locked by another thread. So waiting happens if the thread is waiting for a particular resource to have a certain value. So now don't get confused. Synchronization and waiting for a value are two separate things. Now let's try to understand this guarded success method. Now it is synchronized. That means when a thread gets access to this guarded success method, it has exclusive access to the corresponding object. Now after getting the exclusive access to the object by acquiring its block, then it checks the value of this success variable. Now this variable is, if it is not currently set to true, then our thread can't operate even though it has the exclusive access. Then what does it do? It calls a wait method and go to the wait state. Now as you can see here, while the thread is waiting, it can be interrupted by another thread. In order to handle that situation, we must add the logic to catch the interrupted exception as we have shown here. So now the thread is in the waiting state. Now suppose so when the thread goes to waiting state, it will release the lock that is holding. In other words, when it comes to the while loop, it is still holding the lock. Why? Because it is inside the synchronized method. So when it is going to the waiting state, there's no point of holding the lock. Why? Because while the thread is waiting, it is not going to do anything on this object. So when the thread goes to the wait state, the lock that is held by this thread is released. So suppose now a second thread comes. Now since no thread is holding this object, the second thread can get the access to this corresponding object, exclusive access by acquiring the lock. So now it is setting the success variable to true. So when it does that, it will have to notify any thread that is waiting. So waiting, the notification goes to all the threads that are waiting, and one thread by in a random manner will be restarted or taken out from the wait state by the scheduler. So remember, if you want, you can call the notify method on a particular thread that is waiting on this object. However, the better option is to notify all the objects, and one of them will be given the chance to access. So now whatever the thread that was taken out from the wait method, again we'll have to start from here where it executed the wait method, and then it will come when this while loop is executed again. Now it will realize the success variable has been set, and it can now execute the rest of the code without having to go into the wait method again. So remember, success is just a variable name I have used. So here what you have to put is some variable that is true or false. That means we have to give a Boolean variable. So now this synchronization and guarded blocks together can be used to implement this very famous concurrency problem called the producer-consumer problem. So producer-consumer problem means you have a shared resource, and the producer puts values to the shared resource, and the consumer takes values out from the shared resource. So very good example would be let's say a queue or a stack, where the producer puts values to the queue, and the consumer will be taking values out from this queue. So we have to guarantee that the producer and the consumer, and in some cases there can be more than one producer or more than one consumer. So when there are, let's say the simple case, a single producer and a single consumer. So when this shared resource is there, our producer will be one thread and our consumer will be another thread. Now, what will happen if both producer and consumer can operate on this queue or this data structure at the same time? It may run to memory consistency errors. That means, so before the producer actually puts a value, the consumer may try to read. So, and while the producer is in halfway, the consumer will start to access the same memory location, which is not a desirable situation. And also, if your queue has a limited size, we have to guarantee that the producer does not try to put values when the queue is full, and similarly, the consumer does not try to take out values when the queue is empty. So they are two separate problems, right? So first, we have to make sure that producer and consumer are not operating on the shared resource at the same time. And second, we have to guarantee that the producer is not putting values when the queue is full, and the consumer is trying to take values from an empty queue. So in order to satisfy both these requirements, we need locking mechanism on the queue and the guarded blocks as well. So what should we do to implement this producer-consumer problem in a multi-threaded manner? So as I told you, we have the shared resource, and we have the producer thread and the consumer thread. So when either the producer or the consumer wants access, it should be given the exclusive access to this shared resource. How can we do that? So the access methods, that means adding values and removing values, these methods can be synchronized so that whatever the thread that accesses this method, a single method will have the exclusive access to this object. So then any other thread that tries to access this shared resource will get blocked. That means they go to the block state. And then in order to guarantee that this queue is not accessed by the producer when it is full. And similarly, the queue is not accessed by the consumer when it is empty. We can introduce guarded block. So remember, when we add the guarded block, what do we add? We add the while loop, and its execution is determined by a Boolean value. So in this case, what should be the Boolean value? For the producer, it has to wait when the queue is empty. Sorry, queue is full. So producer has to wait when the queue is full. Similarly, the consumer has to wait when the queue is empty. So how do we change this guarded block logic? So here we synchronize two methods, the put method to the queue and the take method from the queue. So now suppose this is the put method, and let's say our producer, only the producer will be calling the put method and the consumer will call the take method. So the producer calls the put method, and since it is synchronized, it will get the exclusive access to the queue object. Now what will be our condition for this while loop? While queue is full. So you can check the size of the capacity of the queue, and if it is full, the producer will wait. And similarly, there's this other method, the take method, which is synchronized. Now, if the producer notices that the queue is full, it is going to the wait state and it is releasing the locking task. Then will come the consumer. It tries to execute the take method, which is also synchronized. Then it will get the exclusive access to the whole queue object. Then what does it check? It checks whether the queue is empty. Now, if you take the queue, it is now at this stage it is full. So queue cannot be empty and full at the same time, right? So if the queue is full, that means the queue is not empty. So for the consumer in the take method, our while loop will have the condition queue is empty. So in this current situation, the queue is not empty. So our consumer will not go into the wait method, wait state, and it will simply pass through it and execute. And after that, it will call the success, notify success. That means it will notify all the threads that are operating on this queue object. So now all the threads that are waiting on this queue object. So now who is waiting on this queue object? Our producer. So now producer is sent the message, okay, now you can come out of the wait state. Now here, in this simple case, only one producer is waiting, so it will be taken out from the wait state. And it will get the, if no other thread has got the exclusive access to the queue object, it will get the exclusive access and it will start from where it stopped. And this while loop is executed again. Now what does it check? It checks whether the queue is full. Now the queue is not full. Why? Because the consumer took out one element from the queue. So now this while loop is not holding. So our producer will come out from the while loop and carry out its normal execution. So that is how we implement this famous producer-consumer multithread problem using the synchronized methods and guarded blocks. So with that, we conclude this lecture. And in this lecture, we learned the several issues with respect to multithreading, and we learned some solutions. Specifically, we learned the concept of synchronization. And we learned that synchronization may lead to some liveness problems, and we discussed that we have to be very careful when we are implementing multithreading applications that have shared resources. And finally, we learn how we can implement the producer-consumer problem using this synchronization concept and guarded blocks. So this marks the end of this lecture and also the end of this course module. Thank you very much.